Angular momentum. You are familiar with linear momentum as the product of mass and velocity. It is a vector quantity and is conserved. Angular momentum is a property of rotating objects. It depends on the angular velocity and on the distribution of mass of the object. It too is a vector quantity and is also conserved. Here we have two rotating objects. If these two objects have the same mass and the same angular velocity, the one on the right has more angular momentum as the mass is distributed further from the axis of rotation. This distribution of mass gives a body what is called its moment of inertia. To work out the moment of inertia of a body, we need to understand torque. Torque, or turning moment, equals the product of the force and the perpendicular distance between that force and the axis of rotation. So here we have a bar which is pivoted at this point here, and a force F acts at this point. This angle is theta, and the length of the bar I've called d. So this length here will be given by d sine theta, and this is the perpendicular distance from the force to the pivot point. And so the torque, T, is equal to Fd sine theta. The units of torque are Newton meters, the same as the units for work. However, the two are not interchangeable, as for torque, the force and the distance are perpendicular, whereas for work, the force and the distance are in the same direction. For linear motion, we know that force is equal to mass times acceleration. For circular motion, there is an equivalent expression that the torque is equal to the moment of inertia multiplied by the angular acceleration. In symbols, we can write this as torque T is equal to moment of inertia I multiplied by angular acceleration alpha. This gives the definition of the moment of inertia as the ratio of torque to angular acceleration. Rearranging the equation, moment of inertia is equal to torque over angular acceleration. Angular acceleration, as you might expect, is equal to the rate of change of angular velocity, which we can write as angular acceleration alpha is equal to the change in angular velocity over the time taken. Other comparisons between linear and angular motion are possible. In this table, I'm going to run through some linear quantities and the equivalent angular quantities. First, mass. Well, this is normally given the symbol lowercase m, and the SI unit is the kilogram. The angular quantity, which equates to mass, would be the moment of inertia. This, as we've seen, is given the symbol capital I, and the units are kilogram meters squared. The linear quantity of distance is normally given the symbol s, and is measured in meters. This would equate to an angle moved through, which is normally given the symbol theta, and would be measured in radians. The linear quantity of speed, or velocity, is normally given the symbol v. Measured in meters per second, the equivalent angular quantity would be angular speed or velocity, which is given the symbol omega, and is measured in radians per second. Acceleration is given the symbol a, and is measured in meters per second squared. The angular quantity we've just met is angular acceleration, given the symbol alpha, and measured in radians per second squared. The linear quantity of force is given the symbol F, and is measured in newtons. The angular equivalent would be torque, which, as we've seen, is given the symbol T, and is measured in Newton meters. . And finally, the linear quantity of momentum is given the symbol p and has units of kilogram meters per second. The angular quantity is angular momentum, given the symbol L and has the units of kilogram meters squared radians per second. Knowing these equivalent quantities allows us to convert our linear equations into equivalent angular equations. So for example, F equals ma, force equals mass times acceleration, can become torque is equal to moment of inertia multiplied by angular acceleration. Momentum equals mass times velocity becomes angular momentum is equal to moment of inertia multiplied by angular velocity. Work done is equal to force times distance becomes work done is equal to torque times angle. Kinetic energy is equal to half mv squared becomes rotational kinetic energy is equal to half angular momentum multiplied by angular velocity squared. V is equal to u plus at, one of the equations of constant acceleration, becomes omega 2 is equal to omega 1 plus alpha t. So omega 2, our final angular velocity, is equal to omega 1, the initial angular velocity, plus the angular acceleration multiplied by the time taken. The equation v squared equals u squared plus 2as has the equivalent form omega 2 squared is equal to omega 1 squared plus 2 alpha theta. S is equal to u plus v over 2 times t will become theta is equal to omega 1 plus omega 2 over 2 times t. S is equal to ut plus a half at squared becomes theta is equal to omega 1t plus a half alpha t squared. And finally, power is equal to force times velocity becomes power is equal to torque times angular velocity. Don't worry if all this looks quite complicated. All these formulae do appear on the datasheet.